morning, students. Welcome to the new session of fluid machinery. And today we will be dealing with reciprocating pump again, and this is lecture 6. And let me go to the contents. The contents are variation of velocity and acceleration in the suction and delivery pipes, then effect of variation of velocity on friction in the suction pipe. So we will be dealing with a single acting reciprocating pump, and these are two derivations which are important in the exam point of view, which includes variation of velocity and acceleration in the suction and delivery pipes, and the effect of variation of velocity on friction in the suction pipe. Now, before going to the first derivation, which is variation of velocity and acceleration in the suction pipe and delivery pipes, we have to learn few things, and you must bring the diagram of a single acting reciprocating pump in your mind and try to correlate these points with it. The piston inside the cylinder reciprocates. Reciprocates means it moves from left to right and then right to left. So a to and fro motion is a reciprocating motion. The piston inside the cylinder reciprocates. It moves from extreme left to extreme right during suction stroke, and it moves from extreme right to extreme left during the delivery stroke. Yes, the piston moves from extreme left to right during suction, and it moves back, which is from right to left during the delivery stroke. At the extreme left, the velocity is 0. So when it at the extreme left, or in the beginning of the suction stroke, the piston is actually at rest, so its velocity is 0. And at the extreme right, so at the extreme right also the velocity is 0. At the extreme right, the piston almost stops and starts its delivery stroke. So at the extreme right also the velocity is 0, and at the mid position the velocity is maximum. So where is the velocity maximum in case of a piston cylinder mechanism? Let be any piston cylinder mechanism, the velocity will be maximum at the mid position. So at the mid position in the cylinder the velocity is maximum. So what does this mean? That is, the velocity is from increasing from 0 to a maximum value, and then it is decreasing from a maximum value to 0, and it is again from a 0 to a maximum value it is reaching, and it is reducing from the maximum value to 0. So this means that there is variation in velocity. So when there is a motion that is having a variation in velocity, it is called an accelerated motion. So it's clear that the piston is accelerating when it moves from the left to the mid, and decelerating from mid to the right during suction. It's clear that the piston is accelerating when it moves from right to mid and decelerating from mid to the left during delivery. So these two are clear from these 3 points. So inside the cylinder, what is happening is the movement of the water is exactly coherent with the movement of the piston. So water also accelerates and decelerates inside the cylinder. So inside the cylinder, see, inside the syringe we have seen the blood actually moves like how the piston of the syringe moves. Similarly, inside the cylinder the water is having a coherent motion with the piston, hence the water moves exactly like the piston, and the velocity of the water in the cylinder will be also equal to the velocity of water in the velocity of water in the cylinder will be equal to velocity of the piston, since these two motions are similar. Now due to this movement, a pressure head due to acceleration is created. So we have heard that there is a pressure head, and this pressure head is P by rho g. This is always attached with a fluid in motion, and here there is another term called the pressure head due to acceleration, and it is created by this accelerated motion, and we will find out its value. So in the examination, what is asked is find out the pressure due to acceleration in a single acting reciprocating pump. Then you need to determine this value. Now how to find out that? To find out that, we will go to its derivation, and where is it? From videos, and here. Yes. Now, when this derivation is asked, first you need to draw a diagram of a single acting reciprocating pump, and this is the cylinder, this is the piston, this is the piston rod, this is the connecting rod, this is the crank, and this is the suction pipe, and this is the delivery pipe. So this dotted shows the initial position of the piston, and this is the position of the real-time motion. Means this is the position of the piston at this particular moment. Means the piston was here, and after a time t it has reached here. Similarly, the crank was here, and after a time t it has reached a position E, and it has turned through an angle theta. When the piston has moved through an angle through a displacement x, it has moved through an angle theta, and omega is the angular velocity of the crank. So these are the initial preliminary information regarding this diagram. Now, omega is the angular velocity of the crank in radians per second, okay, and A is the area of the cylinder. This capital A is the area of cross section of the cylinder, which is, if the diameter is d, then it is pi by 4 into d square. Then A is the area of the pipe. Both we are taking the suction delivery pipe having the same area, so area is, and it's represented by small a. Now L is the length of the pipe of suction or delivery. So L, see, we are here taking both the suction and delivery pipe of the same length, hence the small l represents the length of suction or delivery pipe. Then R is the radius of the crank. This is all given here. Now what is this X? See, there is something to explain here. This is the displacement of the piston after a time interval t, and this is the crank has moved from A to E. Now if you draw a perpendicular from E to this line, which is F, and if you find AF, this AF will be equal to X. Now in the beginning the crank is at A, which is called the inner dead center. So in a horizontal engine, the extreme left is called inner dead center, and the extreme right is called outer dead center. And the piston in the cylinder at a position shown by dotted lines. The crank is rotating with an angular velocity omega. Let in time t seconds the crank turn through an angle theta, and that is the crank moves from A to a point. What is that point? I think it is E. A to E. The displacement of the piston in time t is x, and it is shown in the figure. Now theta is the angle turned by the crank through in time t seconds. What is theta? Theta is omega into t, which is distance equal to speed into time. In case of rotation, theta will be equal to angular velocity into time duration t. Now the distance x travelled by the piston as given. This x, how to find out x? In this diagram, if you see this x, it is equal to AO minus OF. AO minus OF. Now what is this OF? And this is theta. Then this is the adjacent side. Cos theta equal to adjacent by hypotenuse. So cos theta is equal to OF by R, and hence OF equal to cos theta into R. So x will be equal to AO minus R cos theta. This AO is R. AO is the radius, so it is R minus R cos theta. Let's see if it's correct. So x equal to R minus R cos theta, and what is theta? Theta equal to omega t, so it is R minus R cos theta. Now how to find out velocity of the piston? So if x is the distance travelled by the piston, or it is the displacement of the piston, then to find out velocity you can find change in the displacement with respect to time. So velocity is dx by dt, and we know that x is R minus R cos omega t. So differentiate that. How will differentiate? D by dt of R, this R is constant, so it will become 0, and minus d by dt of minus R cos omega t. Minus R can be taken out. Cos omega t, differentiate, you will get minus sin omega t. Then omega is omega t, you have an omega. So minus minus plus, then R sin omega, R omega sin omega t. Differentiate that, you will get it. R omega sin omega t. Now from continuity equation, the volume of water flowing into the cylinder per second is equal to the volume of water flowing from the pipe per second. Means you consider that in a continuity equation A1 V1 equal to A2 V2. So if the volume of water flowing through the pipe and entering the volume of the water flowing through the pipe will be equal to volume of the water in the cylinder or entering the cylinder. Similarly, the volume of the water in the cylinder will be equal to volume of the water entering the delivery pipe. So continuity equation means the discharge equal to constant Q1 equal to Q2 or Q1 equal to Q2 or area into velocity of water in this pipe will be equal to area of the cylinder into velocity of water in the cylinder. So volume of the water flowing per second is discharge. That is why I said discharge. So what are the two things? Cylinder and the pipe. So we have to consider the discharge in cylinder and the pipe. What is the discharge in the cylinder? It will be the area of the cylinder into velocity of water in the cylinder, right? Now what will be the discharge in the pipe? It will be area of the pipe, small a, into velocity of the water in the pipe, which is small v. So what can we write for the velocity of now velocity of the water in the okay, here it is written velocity of water in the cylinder will be equal to velocity of water of the velocity of the piston. That we have already explained. Why? Because the water moves exactly like the movement of the piston inside the cylinder. So you can write small v equal to capital V into A by small a, which is equal to capital A by A into capital V. Now what is this capital V? This capital V is derived here. It is omega r sin omega t. So it becomes A by A into V, which is A by A into omega r sin omega t. So this is what is done till here. Okay, we just remember yourself that first we wrote expression for x, which we got as r minus r cos omega t. Then for velocity we differentiated that and we obtained the equation for velocity. Then we applied continuity equation and we said the volume of water in the pipe will be equal to volume of water in the volume of the water per second in the pipe will be equal to volume of the water per second in the cylinder. Then we took the area of the cylinder and velocity of the water in the cylinder and equated to area of the pipe and velocity of water in the pipe, and you wrote the expression for velocity of water in the pipe and you got it as A by capital A by small a into omega sin omega t. Now if you have the velocity of water in the pipe, you can actually find out the acceleration of water in the pipe. How to find out acceleration of water in the pipe? You differentiate that velocity with respect to time. So dV by dt, again dV by dt of A by A omega r sin omega t, which are the constants? Capital A constant, small a constant, omega constant, r constant. Sin omega t you have to differentiate. Sin omega t you will get cos omega t, and after the omega t you will get omega out. So A by A into omega square r cos omega t, that is the acceleration of the fluid in the pipe. Now what is the mass of the fluid in the pipe? Mass of the water in the pipe, it is density of water into, what is density? Mass by volume. So mass is density into volume. So density into volume of water in the pipe. So the volume of water in the pipe will be equal to the area of the pipe into length of the pipe, right? So it is density into A into L. So rho AL is the mass of water in the pipe. Now how to find out force? If you have mass and acceleration, so you know that which term is going to come after that is force. It will be the multiple of m and a. So you can write rho AL into this term, A by A into omega square r cos omega t. That is a force. Now if you have force, you can find out pressure. Then if you have force and area, you can find pressure. Then intensity of pressure due to acceleration will be the force divided by the area of the pipe. So force equal to accelerate the water divided by area of the pipe. That is rho AL into A by A omega square r cos omega t by small a. You will get rho AL into A by A omega square r cos omega t, and it will be equal to rho L into A by A into omega square r cos theta, right? Now what is pressure head? If this pressure is to be converted to head, you have to divide by rho g, and this rho g is nothing but the weight density of the liquid. So HA equal to intensity of pressure due to acceleration by weight density of the liquid, which is rho L A by A omega square r cos theta by rho G, which is L by G into capital A by small a omega square r cos theta. Now this pressure head in, if the length and the area are different, then the acceleration will be different. So you can write the pressure head due to acceleration in the suction delivery pipe as pressure head due to acceleration in the suction pipe equal to length Ls by G into A by As into omega square r cos theta, and similarly pressure due to acceleration in the delivery pipe will be equal to LD by G into A by AD into omega square r cos theta. Now we know that these things are constant for a, see, out of this rho is constant, L is constant, A is constant, this A is constant, omega is constant, R is constant. So the variation is happening with respect to theta. So here when theta is equal to 0, this pressure head due to acceleration is maximum. Why? Because when theta is 0, this becomes 1, and L by G into A by A omega square R is maximum. Okay. Now when theta is 90 degree, this becomes 0 because cos 90 is 0. This becomes 0. And when theta is 180, this becomes a negative value because cos 180 is minus 1. Hence it is minus L by. So if you are asked to find out, the maximum value of pressure head due to acceleration, it is when you should write when it is when theta equal to 0 and HA equal to this equation, and you substitute 0, this becomes 1, and it is L by G into A by A into omega square R. This is the derivation. Now we have this one, the effect of variation of velocity on friction in the suction pipe. Now that we have to derive. Okay. Now the velocity of water in the suction pipe or delivery pipe is given by the equation V is equal to, that we have already derived, right? V equal to A by A omega sin omega t, or omega t they have taken as sin theta, omega t change it to theta. Then loss of head due to friction in the pipe is given by, since this flow is not a laminar flow, and we have to use the Darcy-Weisbach equation, which is HF is equal to 4 of L V square by D into 2G. It's a turbulent flow, or it is a SHM. The flow is not laminar, it is simple harmonic. If almost a vibratory kind of motion. So you have to use this equation, which is HF equal to 4 of L V square by D into 2G. If it was a laminar flow, you could have used Hagen-Poiseuille, but it's not a laminar flow. You have to use the Darcy-Weisbach 4 of L V square by D into 2G. So F is the coefficient of friction, L is the length of the pipe, D is the diameter of the pipe, and V is the velocity of water in the pipe. So this is the effective variation of velocity and friction in the suction and delivery pipes. Okay. So we have to talk in terms of pipes. So HF you substitute, it will become equal to, instead of V you substitute this A by A omega square sin theta the whole square, it becomes HF equal to 4 of L by D into 2G into capital A by small a into omega r sin theta square. So the variation of HF with theta, this since the square term, the variation will be parabolic because it is a square term. So when it comes to square, it is a parabolic. The loss of head due to friction in suction delivery pipes is obtained using the equation. Then if it is suction, then it becomes HS and DS, and here AS, and if it is HD, it becomes LD, DD, and AD, like in the previous case. Now when is the head, so we know that this variation is actually with respect to theta because all the rest are constants. So the theta, you put theta equal to 0, sin theta becomes 0, and HF equal to 0. So the least value of friction is when theta equal to 0, and when theta is equal to 90, this sin 90 there is another condition also. So when theta equal to 0 and 180, you have no head loss due to friction. So when theta equal to 90, sin 90 equal to 1 and this is maximum. So maximum head loss due to friction is happening when theta is equal to 90 degree. So maximum value of friction is when theta equal to 90 degree, and the value is 4 of L by d into 2g into capital A by omega r the whole square. So this is the derivations. I think these two are easy. After learning this, you must try yourself and without draw the diagram and try to derive that by yourself. Okay, so thank you, and we'll be dealing with in the indicator diagram in the next class. So thank you so much.